Good morning from the Department of Mechanical Engineering in the University of Botswana. I would like to greet you as Lekwete. I was with my co-author or my colleagues, Godfrey Molwakota and Dr. Megbazeleke, on the performance analysis of thermoelectric generators using MATLAB. So here we have the presentation outline, which would follow. So in summary of what we were doing, what we have achieved is that we found that the main difficulty with thermoelectric generators was that solving them for using thermoelectric equations emanated from the fact that operation was based on external temperatures and the junction temperatures, which are the effective temperatures which produce the power output or the performances as were known, were not known. And this article employed the use of the thermoelectric generator design and simulation, which uses an iterative technique to determine the temperature losses to compute the thermoelectric performances using the MATLAB software. Now, the efficiency of this technique was validated using a commercially available thermoelectric module, and the effective junction temperatures which were generated deviated by over 30% of the input temperatures, of which the difference was attributed to the difference in techniques applied by the manufacturer and by our team. So the basics of what we are talking about, what are thermoelectric generators? Now, these are devices that use a temperature difference from a hot side, which require a hot side and a cold side to generate electricity. And their ability to do this is governed by this dimensionless figure, the figure of merit ZT, which is a function of the materials or the thermoelement materials, thermal conductivity, electrical resistivity, and the Seebeck coefficient. Now, the challenge which researchers had was finding materials with low thermal conductivity and electrical resistivity, which govern the validity or the legibility of a material to be assumed or to be determined to be able to be used as a thermal element or a thermoelectric leg. Now, most of the research that was done from there was mainly based or mainly biased to space application, because their concern was accessibility or reliability rather than performance, because the materials which were available had the materials which were available showed low performances, but for the application of space or space application, the concern was more for the availability of electricity, which they could use the availability of the generation of heat in space rather than how good of a performance the materials portrayed. Now, after space application, much of the work that was done was in vehicular waste heat recovery, which was made possible by the availability of funds from these commercial vehicular companies such as BMW and Toyota, to name a few. However, progressing the TEG technology has been applied alongside the traditional renewable energy sources, and it has gained momentum in the energy generation field. So the recent developments or the recent focus on the performance of the thermoelectric generators, it highlighted the high inefficiencies that are seen when operating or when using the thermoelectric generator. Now, the modeling that was done in the previous researches or in the previous literatures used approximated junction temperatures, which only knew or which only factored in the external temperature, the external heat source and the external heat sink temperatures. As thus, most of the models estimated the performance parameters being your voltage, your power, and efficiency, because they neglected the passive elements resistances. Now, in reviewing what or the accomplishments of the previous researchers, the models which were created or which were tested and made, they used the constant thermoelectric properties, which neglected an important parameter such as the Thomson effect. One other model averaged the thermoelectric material properties between the cold and the hot side. And some other model assumed the Thomson coefficient as temperature independent, which in fact was found to be temperature dependent. And the averaged Seebeck coefficient was used in other models instead of the true temperature dependent one. Now, looking at the heat losses, this particular researcher, Ganimba, found that radiation and conduction with heat loss, considering the heat loss mechanisms, found it significant, which contradicted the work of a previous researcher who had bound them or deemed them insignificant. Now, most of these neglected the operational and the effective junction temperatures, which then overestimated the model efficiencies which they had produced. Now, if you look at this, you'd find that the material properties were either averaged or were made constant or were made temperature independent for a temperature dependent module. So when you consider those points, you'd find that a lot of neglect was factored into the modeling, which then creates a distinction will create a large difference when you now move from the theoretical model through to the experimental model, because the experimental models actually shows how much, like it shows the practical part of to the losses, the working capacities of the module, which now differs a lot from the modeling. So improving the modeling and the parameters which are important, or factoring in those little points which were neglected in previous studies, helps close the gap from the difference of the theoretical and the experimental modules. So now the thermoelectrical generator working principle was discovered by this man called Seebeck and coined it the Seebeck coefficient, the Seebeck effect, and the Seebeck coefficient was termed from this, which acknowledges the generation of electricity from the application of heat through a thermal element or thermal element module to a cold side. So what is required is a hot side and a cold side, a hot source and a heat source, a cool sink. Yes, and the opposite was coined by Peltier as the Peltier effect, where you induce a current or you provide a current through a thermoelectric element, and temperature differences are displayed as shown in the schematic on the right. Now, okay, some applications in the thermoelectric generator department. We receive, these are not all of them, these are just part of them. Most of the application was for waste heat recovery, which featured the automotive vehicles and the industrial chimneys, because the industrial sector loses a lot of heat through a lot of exhaust heat, let me just say that. And then some other applications include the wearable and the flexible TEGs, which are factored into the pacemakers, the hearing aid systems, the motion and pressure sensors. Pressure sensors being heat, yes, which also cater for the wireless communication and advanced sensor network. Renewable energy generation, which is used in geothermal systems, geothermal energy systems, and the solar powered systems. And on your left, you can see the figure above, which shows the flexible wearable thermoelectric generator, which utilizes the body heat. So you could see that there's a various, or there's a diverse application range, because when you look at industrial waste or industrial heat that is generated, it comes at a temperature difference of around 3 to 500 degrees, and the body emits a temperature of about 37, 36. So, and 37, 36 with the ambient temperature being around 25. So the difference is around 10 to 15. So you could see the diverse application range of the thermoelectric generators. So in improving the modeling, in improving the parameters which affect the performance, you get something that features an application through a wide range of power generation systems.
Sorry, you would normally have 5 minutes. Our next speaker, Okay, so you can continue.
5 minutes.
Well, as our next speaker isn't here, you can continue, but you would normally have 5 minutes. Thanks.
All right. Okay. So what we did was use the thermoelectric design simulator in the MATLAB application. And we considered the passive elements from the ceramic plate, the electrode, the contact pad, and the interface materials. And we used that to calculate the effective junction temperatures and the temperature dependent material properties of the scatterudites, which are labeled below. The N-type and the P-type were used. We did a parametric study for the height and the cross-sectional areas. We varied the height for a module or for a thermal element length of 1 to 10 millimeters. That should be millimeters, not millimeters squared. The height from 1 to 10. The area from 1.5 to 12.5. For the symmetrical module, we did 3 simulations for the area for a symmetrical module and for the non-symmetrical module, where we varied the other legs area and we kept the other one constant. Thermal losses, power output, and efficiency graphs were generated and discussed. So this is the schematic of what we were working on, and these are the parameters, or these are the legs which we had varied. This is the electrode pad, and it's transparent for just for visual purposes. So these are the thermodependent material properties. And you can see that through the area of operation, or through the length, or through the temperature, the range of operation for the temperature from 300 kelvins to 800 kelvin, you see that the properties or the material does not behave linearly, or it changes with increase in the temperature, which is one of the important factors that affect the performances in which we are to discuss. So, yeah. Now we have the effects of the variation of height onto the thermal losses. We can see that at a shorter height, there's a lot of, or there's a high temperature differences at the junction. What we did was take the external temperature and the simulated junction temperatures, and we found the difference between them. And these are the losses experienced at this height. These are the losses experienced throughout the variation of the heights. So you can see that with a shorter leg, or shorter thermal element leg, there is a higher temperature loss, or a higher temperature difference for both the hot side and the cold side. So the shorter leg length, the shorter the leg length, the higher the thermal conductivity, but lower electrical resistivity. This is what we would want, because when we have, this is what is contrary to what we want, because we would want something with a lower thermal conductivity and a lower electrical resistivity, because lower thermal conductivity allows the accumulation of heat, which allows temperature differences to stay the same. And when the temperature difference is very high, you'd find that there's a higher output of the power and the efficiency. So the longer the TE legs, increase overall thermal resistance, hence the decrease in the thermal conductance, which is seen by the graph on your left, on the left of your screen. The low conductance results in the large thermal difference, as I had mentioned, thus a difference in the heat flux. The heat flux which is used, the heat flux from the hot side and the cold side, which is used to generate the power. So a larger power means a large heat flux difference from the hot side and the cold side. So when you increase the volume by increasing the height, it increases the electrical resistivity, hence a drop in the power. I think that is very self-explanatory. And when you see from this graph, an optimum height range for the power production would be around 3 to 5 millimeters. And that is made, or that is justified by the following graph for efficiencies, which 3 to 5 would fall under the 14.92 and the 14.59 range, which is technically where you get a higher efficiency for the relatively high power output. Now, it is important to mention that the optimum parameter for power is different for the optimum parameter for the efficiency, because the thermal element legs differ in the nature, so they behave differently at different parameters or at different material volumes. So the shorter leg length has high thermal conductance, which leads to low junction temperature differences. Now, at the low junction temperature difference means you have low heat fluxes. Low heat fluxes result in the low efficiency. So when you increase the leg length, you increase the heat flux differences, hence you increase the efficiency. And I think that covers those points. That is the parametric study on the height. Onto the parametric study for the cross-sectional area. You'd find that for the three modules, or for the three simulations that we had run, we have the symmetrical module, the variation of the N-type, and the variation of the P-type. The symmetrical module reports or records higher thermal losses because an increase in the thermal mass directly increases the heat absorption capacity, hence the thermal losses as well also. Now, the difference with the P-type and the N-type is that generally due to the nature, because an increase, or when the N-type is found to be universally weaker thermoconductive material as compared to the P-type, hence you'd find a higher thermal conductivity throughout the N-type as compared to the P-type in this situation when you when you vary the area. So yeah. The efficiency generated for the symmetrical module, you'd find that there's relatively no difference because there's relatively no difference because both of the N-type and the P-type are relatively the same area, or they're relatively the same area. So the higher performance generated by the P-type is in a way nullified by the performances from the N-type. And you'd find that with increase in the area, the P-type increases, the P-type efficiency increases, whilst the P-type efficiency decreases, whilst the N-type increases due to the higher electrical conductivity as per the material properties which were highlighted in the previous slides. Now, again, optimized performance occurs at different area values for both the legs. As much as it differs for the variation in height, it also differs for the variation in the area. When we move on to the power generated, you'd find that...
Will you be wrapping up soon, please? Because you are taking quite a long time. Thanks.
Okay, I think I'm left with 2 slides. So
that's fine, then go through the...
Yeah, okay. When you see here that it's for the symmetrical module and the non-symmetrical module, the P-type module, which had the higher area, generated relatively the same power compared to the symmetrical module. But on the factor of production cost, it is optimized when you use non-symmetrical modules because raw materials used to generate these modules is less for a non-symmetrical module than for a symmetrical module, which gives us the benefit and also the relative power that we would require for a module of these areas. So in conclusion, thermoelectricity generation is not a new concept despite the relatively low levels of adoption that have been featured in the past. The use of various modeling techniques and tests allow for the stepwise improvement of the TEG's performance, and this caters for the possible incorporation of the TEG technology into the mainstream and renewable energy mechanisms such as the solar and the geothermal power generation mechanisms. So the study that we have made was just particularly for the parametric study and finding out how the mechanical variation of the thermoelectric generator or thermoelectric module could affect the performance parameters for it. So these findings would help us then to progress forward to incorporate this into the solar thermal energy generation mechanism or energy plants, because they are relatively, in our country, they are relatively an attractive form of renewable energy, and it is widely available. So in that sense, I would like to thank you for having me, and thank you for the opportunity. I think that would be it for me.
Thank you very much.